Hello everyone, welcome back to another video. In this video we take a look at rational numbers as exponents. To begin, let's note the following. Let's say that we had x, or rather the square root of x, times the square root of x. Let's consider what that equals. Well, we know that if we take the square root of something times the square root of that same thing, the square roots effectively cancel and you just get x. So you just get that thing to the first power. Now in order for this to be consistent with the exponent laws that we learned earlier in the term, it would have to be the case that this is the same thing as x to the 1/2. Let me argue that on the side. If we had x to the 1/2 for each of these guys, so x to the 1/2, and we multiplied it by itself, x to the 1/2 times x to the 1/2. You add those exponents together. That's the exponent law we know from section 1.6. We add those two together. 1/2 plus 1/2 is just 1, so we do get x to the first. So this is consistent with our with what we got earlier. The square root of x times the square root of x is just x. So since this is consistent with it, we can just say that any time that we have something of the form a to the 1 over n, it's the same thing as the nth root of a to the first for emphasis. But it turns out we can actually generalize this a little bit further. Say that we have a to the m over n. This is just the same thing as the nth root of a to the m. So you could see us putting an m instead of a 1, it just amounted to that m taking the place of the 1. It's just whatever number's here is the exponent of the radicand. And whatever number's in the denominator of our exponent, this n, that's the index. So that tells you what kind of a root you're taking, a square root, a third root, fourth root, etc. Okay, so now that we've established all of that, we should take a look at some examples. Let's take a look at following example. So what I want to do first actually is I just want to take what we've established right here and throw that up at the top. So that's a helpful formula we'll be using along the way. So let's just say we want to take a look at something like 16 to the 1/2. So 16 to the 1/2 is actually just the same thing as, well, we've got a 2 in our denominator, so that's our index. So we've got the square root of 16. Again, usually we don't really write the 2's for square roots usually, but just for emphasis I'll write it here. Now this just means, what do you multiply by itself to get 16? That's the square root of 16, it's just 4. So 16 to the 1/2 is just equal to 4. Let's take a look at one more example. Say we consider -8 in parentheses to the 1/3. Well, this will be the cube root. Again, that's our index because it's the denominator of the rational exponent. And then we take -8 to the first power inside. Now it turns out that because we've got a negative and a cube root, we come out with a negative because think about it this way, 3 negatives would make another negative. And then the cube root of 8 is just 2. So we've simplified both of those expressions using radical notation and then simplifying afterward. Let's take a look at some more examples, possibly some more interesting ones. So example 2. Let's get used to taking something that's in radical notation already, so something like, say, the 5th root of 7ab. And let's take that and let's take it from the radical notation to exponent notation. Well, notice we've got the fifth root of this single thing to the first power. In other words, we can write this as 7ab. It's to the first power over our index, over 5. So it's 1 over 5. So we've just expressed that in exponent notation. So we went from radical to exponent notation. Let's take a look at another example. Let's look at the 7th root of x cubed y over 4. This is just, notice we've got the 7 as our index, so that means we take what we've got here, and notice this is really just like this to the first power. So we just basically copy what we've got, x cubed y over 4, copy all that down, and then we take this to the 1/7 power. Again, because our index is 7, and then it's raised to the first power for the radicand. So this is what that is equal to. Now that we've looked at a couple of examples, kind of getting used to transitioning between exponent and radical form and vice versa, let's take a look at an example that's probably the most complicated so far. Let's pan down. Let's use a different color just for variety's sake. So let's say we want to write an equivalent expression using radical notation, and then we want to simplify. So let's say we've got something like 27 to the 2/3. All right. So we can write this in radical notation from this exponent notation in the following way. We can write it as, well, we've got a 3 as our denominator, so that's our index. So I'll just go ahead and write the cube root. And then we've got 27 on the inside, but then we've also got to square it because of the 2 in the numerator. So now we need to think of how this can be simplified. And here's where we use some clever tricks that we learned about in the past in section 1.6 actually. So now this is the same thing. Actually, maybe I'll do it right here. This is the same thing as the cube root of 27 is the same thing as 3 cubed, right? So those two are the same. So we can write the 27 as 3 cubed and then just leave the square on the outside. Now in effect, this is actually the same thing as the cube root of 3 cubed all squared. We can basically say we can take the cube root of 3 cubed and then square it after. It turns out this is a legitimate operation here that we're using, a legitimate property that we're utilizing here. And now the cube root of 3, we know from our last video that these just end up canceling out, and we just end up getting 3 squared. And 3 squared we know is 3 times 3, it's 9. Awesome. So basically with these types of problems, we just need to think of clever ways to rewrite what we're given, so that way we can work with it more easily without a calculator. Let's take a look at one more. Say we've got 25 to the 3/2 power. Well, 25 to the 3/2 power. Well, again, let's just focus on the index first. Our index is 2, so we get a square root, and I'll write it in for emphasis. And then we've got 25 cubed on the inside. Now, we would like to express 25 as some kind of a perfect square. So we can think of 25 as 5 squared. And then since we've got a power of 3, we can't forget about that, so I include that as well. And now, again, we're just utilizing that property that we can kind of pull out this 3 and consider the square root of 5 squared and then cube it afterward. But again, whenever we have the square root of something squared, the thing we're taking the square root of is non-negative, so we can just cancel this out. It's really just the principal square root. We cancel these out, and we're just going to have 5 to the third at the end of the day. And 5 to the third is 5 times 5 times 5. 5 times 5 is 25, and then 25 times 5 is 125. So we see that we can take these pretty complicated looking expressions, like 27 to the 2/3, 25 to the 3/2, and provided that it's the right kind of fraction, we can actually simplify it down to these nicer looking forms. 9 and 125 certainly are nicer looking than what we started with. So that's the thrust of this section. Next, we should look at some more examples that use some negative exponents. So that's what we'll do next. So let's kind of zoom out of what we've done so far. Very cool. So I'll pan over here and zoom in. Get example 4. So example 4, this is actually example 5 in the text, but just to stay with our numbering convention. Let's say we consider 9 to the negative 1/2. Let's think about what that would mean. Well, remember what we do with negative exponents. We take what we've got and we just basically move it from, so to speak, we move it from the upstairs to the downstairs. So we take this fraction that looks like this, and we basically rewrite it. We write it as 1 over 9 to the 1/2. We move the 9 to the bottom, and then we make the exponent positive. And now we know 9 to the 1/2 is the same thing as 1 over the square root of 9. I'll probably stop writing in the 2 for emphasis at this stage. The square root of 9 is just 3, so we get 1 over 3. So in other words, 9 to the negative 1/2 just equals 1/3. Let's look at some more examples. How about 64 to the negative 2/3? Well, again, we do the first step of just writing it as a positive exponent, moving it down. Okay, but now we have to think about what is 64 to the 2/3? Well, just using radical notation right away, this is the same thing as the cube root of 64 squared. Now we have to think of how we want to express 64. Well, we've got a cube root, right? So we need to express 64 as a cube root, and it turns out that 4 cubed is 64. So we can just rewrite this one more time. We can write it as the cube root of 4 cubed all squared. And at the end of the day, what's going to happen with this is the cubes are going to cancel, and all you're going to be left with is 1 over 4 squared, which is just 1 over 16. So 64 to the negative 2/3 is just the same thing as 1 over 16. All right. So we've taken a look at some examples with negative exponents, and now perhaps we should just take a look at simplifying some radical expressions by converting them into their exponential form. So this is example 7 in the text, but Just by my convention, I'm going to write 5, go sequentially. So we're supposed to use rational exponents to simplify, and we should not use exponents that are fractions in our final answer. So this is 7a, 5a for us. It's the sixth root of 5x cubed. So we should write this as a rational exponent first. So what do we get? We get 5x all raised to the, okay, now our index is 6, so that goes on the bottom, and then our numerator is 3. Okay, now 3 over 6 is the same thing as 1/2, so we get 5x to the 1/2. And let's just go ahead and bring this back to radical land. Whoops, let's bring this back to radical land. This is the same thing as the square root of 5x. And that's basically as simplified as we can write it. Awesome. Let's look at another example. Say we've got the 5th root of t to the 20th. Well, that's the same thing as t to the 20 over 5. And we know that 20 over 5 is just 4. So I'll leave the answer like that. Notice we don't do a radical form for this one because it would be kind of silly to write the first root of t to the 4th. We usually don't write the first root of anything. But anyway, let's look at example C. Now we're given something a little bit more complicated. It involves a few variables. So we've got the cube root of ab squared c. And now they take this whole thing and they take it to the 12th power. Well, this is the same thing. Remember, whenever it's on the outside like this, we can take it and pull it in. We just have to be careful when we pull it in. So we have to take the entire radicand and take it to the 12th power. So in other words, we've got ab squared c. We take that whole radicand, we raise it to the 12th power. And then our index is 3, so we have 12 over 3. And now this is the same thing as ab squared c to the 4th power, which is just the same thing as, remember our exponent property, we multiply through the exponent. So we get a to the 4th, b to the 8th, c to the 4th. Last example we're going to look at is the following. We've got, here, let me pull this down a little bit actually, letter D. So this is actually the square root of the cube root of x. We've got this kind of nested exponent situation happening, and it's ultimately not that bad to work with. We just have to think about what these are as rational exponents. So maybe first I'll just leave the square root on, and I'll rewrite the first one, the inner radicand here. I'm going to rewrite this, the cube root of x, as x to the 1/3. So that's the first thing I do. And then next I can say, okay, well this is the square root of x to the 1/3. So this is like x to the 1/3 raised to the 1/2. Remember, that's what it means to be the square root of something. You just raise it to the 1/2 power. And now we use those properties of exponents. We multiply here in this case, right? So we just get x to the 1/6. All right, let's take a look and zoom out at everything we've done so far. So we've done quite a few of examples from 7.2. I think this is a good place to stop. If you have any questions, please leave them in the comments or bring them up in class. But otherwise, I will see you all in the next video where we talk about section 7.3, where we are going to end up multiplying radical expressions. Take care.